Imagine the most advanced open-world video game you can think of. The map is gigantic, the characters feel alive, and the physics are unbelievably real. To save processing power, the game is smart. It only renders the world in high detail right around you, the player. The mountains you've left behind might fade into a simple texture, and characters you can't see don't need to be doing complex things. It's all just a trick for efficiency. Now, what if our reality works on the same principle? What if the universe only renders itself when we're looking? This is the core of the simulation hypothesis, an idea that has jumped from the pages of science fiction into the halls of serious academic debate. The argument is surprisingly straightforward. Given the exponential growth in computing power, the odds are we're already living inside a simulation. Stay with me here, because the arguments for this idea are woven into the very fabric of our cosmos, from the tiniest particles to the ultimate speed limit of the universe. By the end of this, you might just start to question everything you think is real. The feeling that our reality might be an illusion is not a new one. It didn't start with the Matrix. It's one of the oldest questions in philosophy. Thousands of years ago, Plato gave us his allegory of the cave. He pictured prisoners chained up, forced to stare at a blank wall their entire lives. Behind them, a fire burns, and people walk by, holding up objects that cast shadows on the wall. To the prisoners, these shadows aren't just shadows. They are reality. They have no idea there's a real world outside, with real objects casting those shadows. Their entire existence is a flat projection of a higher truth. Flash forward a couple of thousand years to the 17th century. The philosopher René Descartes was wrestling with a deep-seated doubt. How can I be sure I'm not dreaming right now? He took it a step further, imagining an evil demon, an all-powerful being whose only goal was to deceive him, creating a perfect illusion of the world around him. For Descartes, everything he saw and touched could be a sophisticated lie. Plato's shadows and Descartes' demon are the philosophical ancestors of the modern simulation hypothesis. They both point to that same gap between what we perceive and what's actually real. For centuries, this was just a thought experiment. There was no real-world technology that could make such a massive deception seem plausible. But then, we invented the computer, and with it, we started building our own virtual worlds, our own caves, our own simulations. As our technology gets more and more powerful, the line between the simulated and the real gets blurry, forcing us to ask that ancient question with a terrifying new plausibility. Are we the ones building the simulations, or are we inside one? The person who dragged this question into the 21st century is Nick Bostrom, a philosopher at Oxford University. In 2003, he published a paper that set off a firestorm of debate. It wasn't a wild theory, but a cold, logical argument that presents us with a stark choice. It's called the simulation argument, and it's a trilemma, 3 statements, one of which, he argues, must be true. Let's break it down, because this is the intellectual heart of the whole idea. The first possibility is that civilizations like ours almost always go extinct before they become posthuman. A posthuman stage is when a civilization gets so technologically advanced it has enough computing power to run ancestor simulations. Simulations of its past that are so realistic, the beings inside would be conscious and have no idea they're in a program. So, option 1 is the doom scenario. We wipe ourselves out, a plague gets us, an asteroid hits. Whatever it is, we never get powerful enough to create these simulations. The second possibility is that any civilization that does make it to this posthuman stage simply isn't interested in running lots of ancestor simulations. Maybe they lose interest in their history. Maybe they have universal ethical rules against simulating conscious beings who can suffer. Or maybe they just have better things to do with their godlike computing power. In this case, the simulators could exist, but they just choose not to simulate us. Now here's the mind bender. The third possibility is that we are almost certainly living in a computer simulation. The logic here is a pure numbers game. If the first two propositions are false, meaning civilizations like ours do survive and they do run ancestor simulations, then what happens? They wouldn't just run one or two, they could run billions. Think of it the way Elon Musk once simplified it. Assume there is one base reality, the original physical universe. If that base reality creates billions of simulated worlds that are just as real as their own, then the number of simulated people would vastly outnumber the people in base reality. So, if you are a conscious person, and you have no way to tell if you're in the one base reality or one of the billions of simulations, simple probability says you are overwhelmingly likely to be in a simulation. Bostrom doesn't claim to know which of the three is true. He just argues that logically, it has to be one of them. So you have to choose. Are we doomed? Will our descendants be uninterested in us? Or are we a piece of code? It's a tough choice, and none of the options are exactly comforting. This is where the theory shifts from philosophy to physics. If our world is a program, shouldn't there be hints in the operating system? Proponents argue that yes, the clues are there, if you know how to look. They suggest that in some ways the universe behaves exactly like a simulated reality would. First, there's a speed limit. An absolute, unbreakable speed limit in our universe, the speed of light. Nothing can go faster. But why? In a purely physical world, why would there be a hard cap on speed? If you think about the universe as a computer, though, a speed limit makes a certain kind of sense. It's like the processor speed. The speed of light could be the maximum rate at which the simulation can update the state of anything in its system. It's the ultimate refresh rate for the cosmos. Second, our reality seems to be made of discrete units. For a long time, we thought space and time were smooth and could be infinitely divided. But quantum mechanics showed us that at the tiniest scales, that's not true. There seems to be a smallest possible length and a smallest possible unit of time, known as the Planck units. You can't have half a Planck length. This has led some to suggest that our reality isn't analog, but digital, made of fundamental units, almost like pixels on a screen. Now, this is a popular analogy, not a proven fact, but it's an intriguing parallel. This brings us to one of the most powerful and strangest arguments, the observer effect in quantum mechanics, famously shown in the double-slit experiment. The gist is this: if you shoot a particle, like an electron, at a wall with two slits, it acts like a wave and somehow passes through both slits at once. But, and this has baffled scientists for a century, if you set up a detector to see which slit the particle goes through, it suddenly stops acting like a wave and behaves like a particle, picking just one slit. The simple act of looking at it changes the outcome. In the context of a simulation, there's a fascinating if speculative explanation: saving processing power. It's the same trick as the video game. Why would the system waste resources calculating the definite path of a particle if no one is looking? It's computationally cheaper to leave it as a cloud of possibilities. But the moment an observer demands to know where it is, the system has to render a result and give it a definite position. Reality, in this view, doesn't bother to be definite until we look. Finally, some physicists are exploring whether the laws of the universe themselves point to a computational nature. The physicist Melvin Vopson, for instance, has recently proposed what he calls a second law of infodynamics. The famous second law of thermodynamics says that disorder or entropy always increases. But Vopson's new and still debated hypothesis suggests that in information systems, the opposite is true. Information entropy tends to decrease over time. He argues this might point to a universe that is constantly optimizing and compressing its own data, exactly what you'd expect from an efficiently running simulation. Okay, let's hit pause for a second. If this is starting to bend your brain a little, that's completely normal. We're questioning the very foundation of reality here. If you enjoy exploring these kinds of mind-bending ideas, make sure to hit that subscribe button. We're all about asking the big questions. Now, let's get back to it. As compelling as this all sounds, let's pump the brakes. The simulation hypothesis is an extraordinary claim, and it faces some major challenges. First off, there's the evidence problem. While things like the speed of light and the observer effect are interesting parallels, they aren't proof. They are interpretations of physics that happen to fit the simulation narrative. For now, there is no smoking gun experiment, no definitive piece of data that says, yes, this is a simulation. This leads to the next big criticism. The theory might not be falsifiable. A good scientific theory has to be testable. You have to be able to prove it wrong. But how could you ever truly disprove that you're in a simulation? If you found a glitch in the matrix, couldn't the simulators just patch the code and wipe your memory of it? Any experiment you design to find the edges of the simulation could, in theory, be manipulated by the simulators themselves. A perfect simulation could be designed to be perfectly undetectable, which might make this more of a philosophical puzzle than a scientific question. Then, there's the sheer computational power required. Simulating an entire universe, down to every single quantum event for billions of conscious people, seems like an impossibly huge task. The energy and data storage needed would be astronomical, maybe more than exists in our own universe. Some physicists argue that simulating our messy, complex reality would be so wildly inefficient that no hyper-advanced civilization would ever bother. Finally, there's a deep philosophical objection. We don't know if consciousness can even be simulated. The whole argument rests on the idea that consciousness can emerge from a computer program just as it does from a biological brain. But we don't know that for a fact. It's possible consciousness is tied to our specific biology, and that a simulated being would just be a philosophical zombie, something that looks and acts conscious but has no inner experience at all. If consciousness can't be simulated, the whole argument that we are simulated consciousnesses falls apart. Despite these challenges, some scientists are actually looking for ways to test the idea. The hope is that no simulation could be absolutely perfect. If our universe is a computation, it might have artifacts, rounding errors, or glitches left over from its programming. One proposed search involves looking for weird patterns in the cosmic microwave background radiation, the faint heat left over from the Big Bang. Scientists are scanning this ancient light for anything that looks unnatural, which might hint at the edge of the simulation grid. Another idea is to study the highest energy cosmic rays. These particles shoot across the universe at nearly the speed of light. The theory goes that if space-time is a grid of discrete points, like pixels, these ultra-high energy particles might not travel smoothly. They might scatter in strange ways that our current laws of physics don't predict. Melvin Vopson has even proposed an experiment based on his infodynamics hypothesis. He suggests that information has a physical mass. If you collide a particle with its antimatter particle, you annihilate them, erasing their information. He predicts this should release specific, detectable photons. Finding them could be the first testable evidence for a universe fundamentally built on information. To be clear, none of these searches have turned up a smoking gun. No confirmed glitches have been found. But the fact that scientists are designing real-world experiments to look for the seams of reality shows how seriously this idea is now being considered. It's moving out of pure philosophy and into the realm of experimental physics. So we've gone from Plato's cave to Bostrom's trilemma, and through the strange world of quantum physics. We're left with a choice of possibilities. Are we a biological fluke in a random universe? A civilization headed for extinction? or characters in a program running on some cosmic hard drive? The truth is, we don't know, and we might never. But that leads to the final, and maybe most important question. If we are in a simulation, what should we do about it? How does that change things? The answer from most people who seriously consider this idea is surprisingly simple. It doesn't. If the simulation is this perfect, this complete, and this indistinguishable from what we'd call base reality, then for all intents and purposes, it is our reality. The love you feel, the pain you experience, the choices you make, all of it is real to you. Your consciousness, whether it's running on carbon or silicon, is the arena where your life happens. The rules of this universe, whether you call them laws of physics or lines of code, are the rules we have to play by. The idea of a programmer doesn't change our lived experience any more than the traditional idea of God changes things for a person of faith. Maybe the simulation hypothesis is best seen as a modern way of expressing our oldest instinct, to ask why we're here, and to be in awe of the strange, beautiful, and deeply mysterious universe we find ourselves in. Simulated or not, the experience is real, and this journey is ours to take. What do you think? Are we living in a program, or is that just a story we tell ourselves to make sense of a universe that's stranger than we can imagine? Let me know your thoughts in the comments below. And if you enjoyed this trip into the nature of reality, please give this video a like and subscribe for more deep dives into the biggest questions out there. Thanks for watching.